This is Chapter 3, Section 3. This is the second video. All right, at a certain college, the probability of a student being enrolled in math is 0.02, 20% essentially. Being enrolled in speech is 65%, and being enrolled in both is apparently 25% using M for being in math and S being enrolled in speech. All right, so let's write the items we have in probability symbolism first, right? So let's do that. So you always want to read the problem first and analyze what the items are in Spanish. Okay, not an and. Probably been enrolled in math given they're enrolled in speech. So that's conditional probability, basically. The condition that if they're in speech already. Okay. All right. Let's determine each of these. Okay. So determine the probability of students enrolled in math and speech. So the probability of math and speech. Okay, so that's clearly a multiplying scenario since it's and. So we'll just copy this twice. Copy, paste, and put a multiply in between. Right, so this is math in the first one and speech in the second one. Except this is a dependent scenario, isn't it? So it'd be math given, speech given math, right? Because we know it's dependent because of this right here. The problem is these are in the wrong order, and these are not interchangeable, correct? These are not interchangeable. So we can change this because the probability of the other way around is the same thing. So let's just copy and paste. We'll do S and M. So speech and math and speech are the same thing as far as the logic goes. So we can do speech here and then math given speech here. Okay, so long story short, as we know from the prior sections, you cannot switch conditional probabilities. They're not the same thing. However, you can switch ands and ors, right? That will work. Okay, so if I do this mathematically, I'm going to get 0.65 times the 0.25, which would be 0.1625, which means they are dependent events, right? Okay, which makes sense. Okay, can you enroll in math or speech? Okay, so we'll do this. So we'll do the math or speech now. Let's shrink this down. There we go. So the probability of math or speech. Okay. So that'd be the probability of math, right? Plus the probability of speech. And you always have to look for the overlap if there is one, right? So that's the probability of math and speech. We'll just take this over to here, copy, paste, and do the and, right? So format, color, blue. Okay, so math was 20%, and speech was 65%, and both, which we already proved up here, right? Either one of these is the same thing, M-A-N-S or S-N-M, is going to be 0.1625. So if I add that up and subtract, that'd be 85 minus 625 would be 0.6875, right? So what does this mean? This means they are not mutually exclusive, right? Because they have an overlap, right? They're not mutually exclusive. So what does this mean at the end of the day? We're not mutually exclusive because we can be both at the same time, right? So any event can be both at the same time, right? Or any trial. And they are dependent. So what happens now is dependent on what happened before. Oops, I forgot an N there. There we go. Okay. All right. So are M and S independent? Well, clearly, the second I see this right here, I know they're independent. They're dependent, right? Because one depends on the other. My guess is there's some kind of prerequisite. You know what I'm saying? That is my guess. Are they mutually exclusive? And no, we just proved that they are not. Which my guess is you can be enrolled at both at the same time is probably possible at this particular school. That would be my guess. Okay, let's try a different problem here. So let's say we go to the library and you can take out a book or a DVD and the following probabilities are given, which is a conditional here. So I want the probability of not B, essentially is what it's asking. So the probability of B naught, right? So the other way of writing it is like this, right, with the bar above it. Okay, put an equals there. Okay, so format, color, blue. There we go. All right, so if B is 40, then not B is clearly 60, correct? All right, so D and B. All right, so we'll math type that up there. So equals the probability of D times the probability of B. Oh, but the problem is I can't do that because it's a conditional, isn't it? So they said to be condition of D, right? That's not going to work because I just noticed if I look here, I don't have that. I have the other way around, don't I? But I can switch this up, right? I can also do, let's go over to here and do the probability of B and D, right? And we do that and D. And that'll be the probability of B times the probability of D given B, right? That'll actually work for us. Now they match up, right? So the probability of B is 40%, and the probability of D given B is 50, right? So 4 times 5 is 20, right? There we go. So that we get there. Okay. And then B given D, right? We don't have. We have D given B. So we could have actually done it the other way if we had calculated this first, right? Which is fine either way. Okay. So equals, shrink that down a little bit so we can actually see it. There we go. So a fraction, this is the probability of B and D, right? Over the probability of D, which is the condition. Or, right, because this is the condition right here, right? The condition, the second thing, which is what happened already, or is the subpopulation. Okay, so make this blue. Okay, so we just figured out in the previous. So D and B or B and D are the same thing. We just figured that out was 20 in the last problem, right? And the population, probability of D is 30. So we can just rewrite that by moving the decimal as 2/3, right? Okay, I like it. We can keep that there. All right, let's try some other scenarios where it's more than 2 events, right? Let's try those. Okay. And clearly in this case, these are dependent events, actually, because obviously there's a change there for the conditional. Okay, so let's say we're drawing 3 cards from an ordinary deck, and the key is we're not replacing the cards. Right? We're not replacing the cards. What's my probability of drawing 3 jacks? Okay, so that's 3 events, right? So I have the probability of a jack and a jack and a jack, right? And you're like, well, it doesn't use the word and. Yeah, but it's implicit. It's not did I get a jack or not. It's did I get a jack and a jack and a jack. Did I get 3 jacks? So you had to get all 3, right? Okay. Then the question you have to ask, since it's an and scenario, this is multiply. Can I simply just multiply this, right? And do jack, right? Put a multiply sign there, right? Paste times paste, right? Are these independent events? No, because there's no replacement, right? So if I don't replace, there are fewer jacks in the deck and fewer cards in the deck, right? So I pull the jack out, so there's 1 less jack. So now, right, and if I pull 2 jacks out of the deck, now there's definitely 2 less here. So you can do it this way. Whoops. Right? Right, because this is or you can also put a subset of parentheses there if you want to, either way, right? Okay, so what does this mean? On the first draw, there's 4 jacks in the deck, right? On the second draw, I've already drawn one. That's the condition, right? That's the event that already happened. There's 51 cards left and only 3 jacks, right? And then the third draw, there's obviously 50 cards left and only 2 jacks left in the deck, right? So that's going to give me 4 times 3 times 12, which is 24, and then that's going to be 132,600, which are dependent events. right? All three are, well, the second two are dependent on the first one, essentially, right? Okay. Yes, you can simplify fractions. I'm sure your second grade teacher would be very happy if you did, but that's not a rule. That's a guideline. It's not necessary. You also don't need to convert to decimals unless otherwise asked for, right? Because the problem is converting to decimals. Sometimes it's rational, sometimes it's irrational. If it's an irrational one, you have to worry about rounding, and we don't want to get into that. Okay, so another similar scenario. Let's say I want to do the different groupings, right? Club, spade, heart, and diamond, right? So I want to get a, let's see here, a club and a spade and a heart. Okay, so equals, I'll make this blue. So the same thing here is, it's still dependent, right? Because there's going to be fewer cards each time. So I can take this, copy, paste. So in the first time I just pull a club and that's it. Nothing special because it's the first one, right? It's not dependent on anything. The second one, however, right, I got a spade, but that depends on me pulling a club the first time. And then the third one is the probability of getting a heart, but that depends on me getting a spade and a club in the prior two pulls, basically, right? You can put second set of parentheses there if you want to, but not necessary. Okay, so remember, if you remember a deck of cards from the prior sections, right? It's 13, 13, 13, 13, correct? 13 clubs, spades, hearts, and diamonds, right? So the probability of pulling a club is 13 out of 52, right? And then if I'm going to pull a spade, but I still have 13 spades left because I pulled a club the first time. But there's 51 cards left, so there are fewer cards. So the probability of getting that spade is actually higher because of the fact there's fewer cards to pull from. And then there's 13 hearts left because I didn't pull a heart yet. I pulled a club and a spade, but there's only 50 cards left, so my odds actually go up for each one because of the fact there's fewer cards in the deck, so better chance of getting it. Okay, so if I multiply that through, I get 2197, and I get the same number, 132,600, right? So again, these are dependent events again. Well, the second two are. The first one is not dependent on anything. Why do I keep doing that? I think my N key is wearing out on the keyboard is the issue. Yes, it is. That is. Okay, well, I guess we're replacing that later. Okay, let's try an OR scenario. So let's say we have a king or a heart, right? So we're going to draw a card. Single card, right? So that's mutual exclusivity. Can you be the same thing at the same time, right? So this is not multiple events. This is one event. So this is the probability of king or a heart, right, which is the probability of a king plus the probability of a heart, right? And you always have to subtract out the overlap, so I'll just copy that and put an and there, right? So even if there's not an overlap, you can still put the and, just make it as 0, you know what I'm saying? Okay, so what's the probability of being a king? Well, there are 4 kings in the deck, right? In hearts, there are 13 in the deck, right? So, is there an overlap? Can you be both at the same time, right? Yeah, there's a king of hearts in the deck, isn't there? There's one of them. All other kings are not heart kings. There's 3 of them, right? But there's one overlap, right? So that one is in here, and it's in here. So it's in there twice. So to subtract out the overlap. So therefore, we have, what's that, 17 minus 1 is 16 out of 52? Right, so this is clearly a not mutually exclusive, right? Not mutually exclusive event, right? It's a singular event, obviously. Okay. All right, what about a red 10? Okay, well, let's copy this here just to save a little bit of time, right? So what about, let's go down here. Go over. I like it. What about a red 10? Okay, so that's a red. Whoops, that's not what I wanted to do. So that's a red 10, right? Minus a red and a 10. Okay, so red cards, there are 13 hearts and 13 diamonds. That's 26 red cards. And there are 4 10s. So the question is, what's the overlap of reds and 10s? Well, you have a diamond that's a 10, or a 10 that's a diamond, and a 10 that's a heart. So there's 2 of them, aren't there? All right, so that's really 30 minus 2, so 28. So clearly, again, this is not a mutually exclusive event, right? Because you can be both at the same time, right? Okay, let's try one more here. How about a face card or prime? Okay, so go down there. Probability of a face card or prime, right? Format color blue. Okay, equals. So we're going to do this plus this. So it's the face card or a prime minus the overlap, which is and, right? Okay, so let's think about our probabilities here. So plus a fraction minus a fraction, and obviously these are all out of 52, right? Okay, so if I think about my prime face cards, that's the royalty, right? Jack, Queen, and King, right? So there's 3 of those and 4 suits. That's going to make 12. And my prime cards are 2, 3, 5, and 7, right? Because all the other numbers in the deck of cards are not prime. So there's 4 of those and 4 suits, so that's 16, correct? Okay, so that's 12 there, and we have 16 here. Well, can it be both a prime number and a face card? No, you're either a royalty card or a number. You can't be both. So that's 0, right? So you don't actually have to put this or this if you know it's mutually exclusive. So my answer is 28 out of 52, right? So we know these are mutually exclusive. It's a mutually exclusive event, right? Okay. Okay. All right. That's the end of that section there. And also, you can list out the items too if you want, right? Mutually exclusive. Okay.